Hello, that's lecture 2 on infiltration. This one is a recording, so we can do some activity in the class. And so to really recap briefly what we have covered with the first lecture in person, we talked about infiltration and went over the idea, or more like, in terms of, we went over the processes that allows water to flow within the soil at the same time as attracting and retaining water within the soil. We talked about the process of adsorption, the process of capillarity, and we have also looked at the fact that water is always flowing from high potential to low potential, so from places where it has a lot of water versus places where it's missing, leading the process of evaporation or infiltration. Now, with this second lecture, I want to cover the measurement and the estimate of time of infiltration, because we can measure, depending on the type of soil, the condition, each soil has a specific infiltration rate, the amount of time necessary for the water to go through it. And so we need to consider a couple of parameters to be able to make that calculation. As you can see from that video that we saw already during the first lecture, as you're adding some water into the soil, the soil will react differently based on its texture and composition to let the water going through. So in terms of parameters to consider, we need to look at what I already called the infiltration rate, which is how fast the speed of the water going through the soil. This will be in relation with what we're calling the hydraulic conductivity, which is how easily a fluid, such as water, will move through a medium, so the soil in its way, that is porous, that has space between the particles that can be either filled up with air or with water. And you see that hydraulic conductivity is as a general definition, because we're using fluid, so we could be speaking about air or liquid water or any liquid other than water, and we're mentioning about porous medium as a soil because the soil is a porous medium. Then once we have that, we need to talk about also what we call the infiltration capacity, which is the maximum rate. So we talked about the infiltration rate, which is how fast usually the soil will go in, the water will go from the surface into the beginning part of the soil. But then after the infiltration capacity, we'll be looking at how the water spread within the soil. And that will depend on a couple of conditions: the surface in itself, if we have an impermeable layer, and at what depth do we observe this impermeable layer, if we have macropores, meaning big holes between grains, big space between the grains in itself, if we have some organic matter that will tend to absorb more water than the particles of the soil in itself. Organic matter tend to have polarity with water, and so they stick more the water to them. And then depending, of course, of the soil texture and structure, which will go over what we call, it's really directly linked with the hydraulic conductivity, which is again referring to how easy it is for the liquid to go through a soil. So once we have defined that, we can start estimating how fast water can go through the soil. And we can estimate that through what we call Darcy's law, which in fact describes how water moves through the through the soil, the ground, as following a difference in distance and in difference in elevation. The equation that we have is pretty simple. It's Q, so the flow rate usually as a volume per second, so like cubic centimeter per second. So it's a volume over time times it's equal to the minus, I don't forget about it, hydraulic conductivity that we talked about, which is how easy it is for the water to go through the soil, the ground. And so this is in centimeter per second, so in distance over time. You multiply it by surface, because it's going through what we call a cross-sectional area, so your volume goes over a specific surface you define, in this case in square centimeter, times a gradient. Your gradient is in fact a fraction with your height, divided by the distance, which in fact, if you're doing that, that's giving you the slope, the angle of the angle that differentiate the level of water from one point to the other point. And so we can make those kind of measurements by digging some wells on specific crops, for example, and by looking at the localization of the water table, we may have an idea of the flow. We can make experiment, and we can also sample some soil, place it in a big pipe, add some water above it, and by looking at the amount of water, see how fast the water will go. Oops, right here. The water will go through the soil. So you're measuring on how fast your water column above the soil will go over a specific distance, a specific depth of soil to evacuate. And so this is related to the hydraulic conductivity, the ease of the soil to let this water going through, which is a function of the porosity, how much space you have within your soil, the pore size, how big those empty pockets between particles in your soil, how big they are, and also how connected are they. So the more connected, such as clay, for example, will not allow the water to go through. It will be difficult. If it's too connected, well, the water will in fact go through very easily. Then it will depend on the viscosity of your liquid, the density of your liquid also too. Okay, so this giving us the idea of the Darcy's law provide us with a flow inside of your soil. And in fact, most of the time, we use Darcy's law not to calculate the flow, but to estimate the hydraulic conductivity. Because from during the experiment on the field, we have easily access to a distance between two wells. We have easily the difference in elevation of the water table, for example. If we're looking at groundwater, we have a pretty good idea of the surface that the liquid will go through, and we can measure the flow. So from that, we usually look for the hydraulic conductivity. This hydraulic conductivity will change depending on the type of soil. So be careful, those scales are reversed between this one and this one. So we do have the hydraulic conductivity expressed on top of it as a log scale right here. So very careful with the log scale, meaning that for usually big grains, particles in your soil, such as sand or bigger than that, like gravels, the hydraulic conductivity will be high. It let the soil going, the water going very easily through it. If you have something very fine, such as sand, such as clay, then in fact you're reducing the hydraulic conductivity. It's becoming more difficult for the water to go through the soil, and so you can see that number right here. So this is your Ku hydraulic conductivity, and you see that you have a high hydraulic conductivity for gravel, sand, silt also, which tend to be big particles of the soil, and as soon as you move to clay, very tiny particles in your soil, well, you have a very small number. So what else can we say with this hydraulic conductivity? Well, in fact, it's driving very much how the water will enter under the soil. If you have a rain event and the rate of your rain event is faster than the conductivity of your soil to let the water going through it, well, what happens is the rain will saturate your hydraulic conductivity, it will saturate your soil, and so what happens is all of your water that is raining right here will in fact be over the capacity of the soil to infiltrate, and you will run off your water. If the rain is precipitating at a slower rate than the capacity of the hydraulic conductivity, then you allow all the water to infiltrate the soil because you're not saturating your system, and so your infiltration rate will be equal to your rain intensity. Okay, so this is a very basic approach on doing infiltration, and that's mostly this Darcy's laws is very used to establish the motion of water in groundwater when they're looking at how the groundwater move from place to place by using wells. Darcy's law is very practical, but it has some limitation. If we really want to look at how the flow, and in fact, the big limitation of this Darcy's law, I forgot to mention, is it's mostly working on saturated soil, which is the case for groundwater, as I was mentioning. Unfortunately, in lots of cases, our soils are not saturated. It depends when you're looking at, but if you're not reaching the water table, you're above it, so you're inside of an unsaturated soil. When your soil is not saturated, you cannot use Darcy's law. It doesn't work well. So you have to make you have to make a derivative from this Darcy's law. And this is what we call the Richards equation. And now we're coming into some crazy equation that I won't been spending too much time on. But you can see that crazy equation right here, which is a differential, which is in fact a derivative, a differential of the Darcy's law, where we find again the hydraulic conductivity, but this is for unsaturated. We call it unsaturated because it's related to unsaturated soil. We have the water content and the metric potential being expressed. But, well, the problem is it's nonlinear, and it's very difficult. It's a very difficult way to solve that equation if you don't simplify it, and simplification tend to be very tricky. So a couple of people have worked on that equation and tried to simplify it. One of the first approach is the Green-Hempt equation that we won't be using neither. It's a simplified equation of Richards, and that's coming from Darcy's law, taking this simplification of the infiltration, simplifying a little bit the derivative to obtain this form, and in fact leading to that form, where the infiltration rate right here is in fact a function of the unsaturated hydraulic conductivity times the initial depth of your water content, of your level of water, times what we call plus the effective suction, how good in fact your the water can go through a soil, divided by the distance on how the at a specific time the wetting front. Remember the difference between what's being wet by the water versus what's dry. We're looking at the distance of over time that has been moved by the infiltration. And so this Green-Hempt equation can be used, but still complicated. The best approach to do it, to measure the infiltration rate, is to use what we call the Phillips equation. Coming from the Richards equation, but coming with some simplification on the condition and the boundary layer, meaning the limits of that. It's considering at the end, I'm skipping all the non-useful details on how they got the equation, but to obtain that, an infiltration at a specific time is equal to a parameter of sorptivity times the time to the power of 1/2 plus a soil gravity parameter times the time. So we are really reducing the amount of parameters of variables into this equation. We just have one sorptivity parameter and then A, which is a soil gravity parameter. So we're obtaining at the end a curve that looks something like that. And we can calculate A and S just by mostly measuring the infiltration over time. We can obtain the curve that will allow us to find S, and A will be found by the extension toward the ordinates. We can calculate, this is, I forgot to mention, this is a cumulative infiltration, so that means that it's the accumulation over time. And so if you want to calculate the infiltration at a specific time, what we call the infiltration rate, not the cumulative one, you will have to simplify that equation, not to simplify, to integrate, to integrate that equation to obtain the infiltration rate. And so you can see that this equation is in fact a basic, oh no, my bad, sorry, I'm speaking a bit too fast. It's becoming late in the day. It's not a derivative, it's not an integration, but a derivative. So by doing the derivative of the Phillips equation above right here, we obtain that equation, which is 0.5 st minus 1/2 plus A. So again, this is a simple derivation from that equation, not an integration, my bad. Again, it's getting late, but I just need to correct that. So that's giving us this curve where we have the infiltration rate decreasing over time, which is something logical we expect to happen because, well, you're still getting more and more water content will not be able to hold that much water, and so the infiltration rate is decreasing. How do we measure that? Well, the main instrument used on the field to measure infiltration is this guy, the double ring infiltrometer. And so it's measuring constantly the infiltration rate and kind of having this kind of simulated the equilibrium of the infiltration by saturating the soil and saturating so the hydraulic conductivity. So we do have this double ring, as you can see, one ring, external ring, one internal ring. Both are filled up with water. First we filled up the first one, the external one, and then we filled up the internal one. Why do we, this ring is in fact, I will share a video, but this ring is in fact fixed deep into the soil. And the idea, by filling up the external ring, we allow the water to flow vertically, but also on the side. As you can see, the motion of water will go vertically on the side. Meanwhile, the center one will only show you a vertical infiltration because it's blocked by the water surrounding it. So we have two different types of measurement with that. We have the direct vertical infiltration rate, which is what we want, versus kind of indirect happening because of the boundary limit. So the external ring is kind of used to limit the potential infiltration from the side, and we're really we're measuring in fact the amount of water that goes vertically, so inside of the inner ring. So again, the outside ring is just to make sure that we have everything under control, and we are like only focusing on the center ring right here. And from that, we can obtain different type of infiltration rate depending on the soil. In this context, for example, the soil is being heavily grazed, moderately grazed, or ungrazed, meaning like mostly a lot of vegetation. And we can see that with a lot of vegetation, you're increasing the infiltration rate. When you don't have, when it's heavily grazed, also potentially compacted, well, the infiltration rate is decreased. So vegetation, organic matter tend to help a lot for the infiltration of water in the soil. When we have those kind of measurements, we in fact need to, and I'm not gonna try to scare you, but we need to analyze those variables or those measurements. So we have right here a table coming out of a measurement from a double ring infiltrometer, where we have the time right here on this column, the amount of infiltration that we noticed every time, and that is cumulative. And so we can already draw our curve of the Phillips equation, the first one I show you. If I'm going back right here, we could be doing this curve by just having those data, because we have the cumulative time right here and the cumulative infiltration. But then we need the derivative of it. So you can calculate the derivative, but I mean, on the paper, and again, I won't be asking you to do that, those crazy equations that I'm not even able to right now at least do, but everything starts with the Phillips equation right here, and you're doing the derivative of it to calculate, in fact, the infiltration rate that you can obtain. So instead of having a cumulative infiltration, which is how much water has been gone over time, like right here, you're taking the derivative and you're finding that the infiltration rate is given right here of 0.3 centimeters per day. That's the infiltration rate. So this is a mathematical solution, but you can do the best way, the most simple way is to do a graphical solution. Again, this is a cumulative infiltration. This is a Phillips equation. So through graphical, it's much easier to solve. All right, and to conclude, at this point, I have considered that water is always infiltrating into the soil. But in fact, we have some soil that do not like water. And you may have observed that. You may have observed those type of soil that it seems that water is just flowing onto it. And those soils are not saturated. What happened is, instead of the water to go and being infiltrated into the soil, in fact, little bit of water will be infiltrating, but over time, there is less and less, and the water will stay mostly on the surface. This is what we call hydrophobic soils. They repel water. Hydrophobic meaning they are scared of water. Phobic is scare. Hydro is water. So they are scared of water. They don't like water. And so they will usually have a specific contact angle with water. So depending on the type of soil, but usually an hydrophobic surface, an hydrophobic soil will produce a contact with water that tend to be easily at an angle over 90 degrees. So we do have a small angle in this case, a bigger angle right here. So hydrophobic angle tend to form those kind of droplet shape. Water tend to form droplet shape on the surface of the soil. They don't tend to make those kind of big flask, pond, whatever, which tend to be infiltrating over time. But the angle that we observe between the surface and the border of the dome, usually for an hydrophobic surface, will make a 90 degrees angle. Why it matters is, in fact, the fact that, well, those soils are not able to absorb the water, so it's very difficult for the vegetation to get access to that water. And in condition of wildfires, we tend to increase, unfortunately, the amount of hydrophobicity, the characteristic of the soil to not be able to absorb, to infiltrate its water. And so before wildfire, we do have a lot of water, no prime, that can go into the soil, but as a wildfire happens, the soil tends to be washed away, accumulation of ash, and in fact, after the new rain coming, the water will not be able to penetrate into the soil anymore and will stay at the surface, running off and leading to potential landslide, potential flooding, flash flooding also too, and that's create a big issue, just because fires tend to induce, for right after it happened, a soil that is hydrophobic, that do not like water. And to end that lecture, I just wanted to show you those microscopic images of a soil surface, a silt soil surface that is hydrophilic, meaning that it likes water, so it will let the water going through it. So we have a wettable silt soil surface right here. You see the angle is close to 0. Meanwhile, right here, an angle of 70 degrees, and in fact, it's a surface that has been treated to be repelling water, and you can see the droplets. So it could be the same surface. One has a product that repel water, and you see this nice little form of droplets. Right here, you can see on a specific metal a drop of water above it. Perfect sphere above that. And again, the prime of wildfires is that water, if it's in a small quantity, well, it's not a big deal, it will evaporate mostly, but if you have heavy rain, it will again lend to landslide, potentially if the water is accumulated at a specific depth, for example, or fast flash flood, and that can be a big issue. With that, we are all done with that lecture. I'll see you in class for some activities. Bye everyone.